Hello, my name is Mike Cease, and I am a student for image processing at the University of Florida. I'm presenting my final project. My research is based on the survey and improvement of visual saliency. So the objective of this research is to just investigate the field of visual saliency, figure out what it really is, look at the current approaches, what have been the latest breakthroughs, etc., how do they apply, and where do the top performers, the top performing algorithms, how do they or how are they architected, and then I wanted to also try to improve the performance of an algorithm. I chose the Boolean map-based saliency or BMS algorithm to improve upon because it is a top performer and the source code was open. So just kind of an overview. Visual saliency is a metric, a visual attribute of images and objects that is measuring how likely the human eye is going to fixate or look at it. So it's kind of the attention factor of an image, and so things with bright colors in a dull environment, things that are moving, weird objects, those might have high visual saliency. Um, it should be noted that visual saliency is not a measure of how important something is, but it's really a measure of how likely is a human going to look at it. And so we're trying to kind of predict the human eye fixations, or what humans would look at, and that's kind of seen as, oh well, that humans, they have some sort of optimal model for looking at things. If we could predict that, we could use that in other algorithms to help out for queuing other algorithms or selecting specific parts of an image. So visual saliency is a pretty new field within image processing. It's kind of a new topic that's been coming about, and there's a lot of new algorithms every year, and there's still quite a bit of improvement that we could do, and we're still kind of, I'll talk a little bit more about this a little bit later on, but we're still kind of working the base case of visual saliency, and there's much more advanced cases that we could start looking into. And so, and like I said, it's been shown that like classification algorithms do get improved by using prediction of eye fixations to help with the classification problem. So my personal motivation for looking into this field is based off of machine learning. I'm very interested in autonomous systems, and technology such as robotics, sensors, and machine learning is rapidly improving. We're seeing year after year more and more research, time and money is being put into these fields, and soon we're going to have robots that can walk or even just roll around, and we already do. We have things like Roombas are commercial products for the personal home. So soon we'll want to actually hook up machine learning algorithms with these robotics to be able to explore unknown areas and start learning about those areas. So visual saliency would be a good approach for figuring out how to cue the gimbal control of a sensor to make sure that we're pointing in the right direction, or even further, how to cue a machine learning algorithm picking out points of it inside of an image coming from the sensor and putting that into a machine learning algorithm to figure out what it is. So kind of what is visual saliency in a little bit more detail. Again, like I said, it's the attention factor, and So we describe visual saliency, at least how we measure it, through a thing called the saliency map. And it's virtually just a distribution of where we predict the eye fixations are. So if we take a look, I'm not sure if you can see my cursor, but if we look at this image, you see a clown. There's an image here, and then going from left to right, these are saliency maps. On the left is the human ground truth. So MIT hooked up an eye tracker to some observers and exposed them to this image for so long and recorded all of their fixations of where the eye is looking at. And so then they created a distribution of those eyes, and that's what this saliency map is of the image right to the right of the clown. And then the next three saliency maps are the three algorithms that I particularly investigated, Deep Fix, then Deep Gaze 1, and BMS, and their predictions of the saliency map. So there's two different types of features within images that visual saliency algorithms kind of focus on. There's low level, which is color, shape, intensity, very low level attributes of an image that's typically seen in image processing. Then there's high level, which is going to be more of your text, faces, anything that's complex, things like signs. That's more high level. Visual saliency algorithms do attack both. Most of the more immature algorithms that are less complex, more simple, are going to focus on your low level attributes. And the high level attributes have been kind of known to be tackled by neural networks, and we'll kind of go into the neural network algorithms in a second. And there's two types of visual saliency. There's bottom up and top down. So bottom up is just purely image based. There's no prior knowledge. The majority of algorithms are investigating bottom up, and we'll talk about it when we get to top down, but it's just much easier to do bottom up than it is top down. Bottom up is if you're given an image with no prior knowledge, just out in the blue, where's the human going to look at? And that's what bottom up. So you're looking at image-based qualities only. Then top down is going to have some prior knowledge. In my paper, I give an example of someone catching a frisbee. And if you knew that a frisbee was being thrown at you, you'd be very likely to look at the frisbee versus maybe something else that would get your attention, given that you weren't known that you didn't know that a frisbee was coming at you. So this prior knowledge would help you figure out where a human would look at if you knew that prior knowledge. But that could be difficult to gather for truth information, and then furthermore, how are we going to test that in algorithms? And I mean, we would have to figure out how to encapsulate the prior knowledge into some form of truth data and use that for training somehow. But we're going to focus in this research on bottom up for now. And then after looking at some things, just a quality that I found in some research is that visual saliency does have a bias near the center. And so that's the center of objects, and also the center of the image. And I believe one of my references in the paper, I think is reference 11, talks about center bias and how it affects human eye fixations. So object-based center bias is going to be, if you see an object, you're more than likely to look at the center of the object and not the entire object. For example, if you had a face, you're probably going to look near towards the eyes and the nose, near the center of the face. You're probably not going to start looking around the ears or something like that. Image-based center bias is, at rest, what image, where's the human looking at? They're probably going to look at the center of the image. That get changes when there's more features in the image, but I've seen that more randomized images, the humans just focus on the center, excuse me, the center of the image. So some related research, the MIT Saliency benchmark is a huge help towards researching this field. They provide 2 large data sets for algorithms to train upon and test against. And I've been focusing on that benchmark website to find my research and evaluate algorithms. And from there, you can see that the people that put together that website, they're actively doing research. The paper I was talking about with center bias is going to be presented at ICCV in 2015. So that's fairly new concept, and research is still ongoing. And so there's a lot of algorithms on that website. And I only kind of focus on the top performers, deep fix, deep gaze one, and Boolean map-based saliency. And go through those. So deep fix is a neural network. This is kind of one of the more top performers on the website, and they claim to be the first fully convolutional neural network that focuses on visual saliency. So what that really just means is that the neural network uses convolution operators. I don't know if you can see my mouse, but on the image here you can see going from the top to the bottom. This is the architecture of deep fix. It goes through some convolution layers, goes through some more convolution layers, and further, and goes down. So they use these convolution layers with parameters as the base of the neural network, and then they architect the neural network with the training data to be able to, for the neural network to find and parameterize the inputs to those blocks of the convolution layers, and be able to make sure that they're doing it optimally to provide the results of the human eye fixations. And so neural networks were kind of an advanced topic. I'm taking machine learning in next semester, so I would like to learn more about this algorithm and see how it could really be picked apart. It was kind of difficult to analyze neural networks and figure out how they're going, but the non-top performers on the website, or the algorithms that are not neural networks, so happen to also not be the top performers and kind of are older algorithms. So I wanted to kind of just focus on the top performers here. And so and we'll see it in the next slide, but they implemented this location bias convolution layer, and they use that to be able to put in their image-based center bias into their images, and this has helped them tremendously in their results. And deepfix was kind of a successor for deep gaze, not by the same person, but deep gaze was kind of the first attempt at providing a high-performing neural network for visual saliency, and uses less layers. It does use convolution. I don't really see my mouse, but the image does go through some layers, and then it goes through some operators. A little less complex, a little less deep of a network, and but you can see here there's a gray image near the bottom that gets fed into a plus sign. That is the way they're doing center bias. They put a Gaussian blob near the center, and then they add that to the predicted saliency map and do a softmax kernel layer for the neural network to be able to provide the more fine-tuned area. So it's more of a linear transformation for the center bias, and the convolution layer that the previous neural network put together was provided a bunch of different Gaussian blobs of different variances. The algorithm would do a parameter analysis. The neural network would figure out which standard deviations and which orientations of the Gaussian blobs do they need to figure out to be able to optimize the center bias operator versus just a linear transformation on all images. And so we saw a little less than optimal performance deep gaze, and I believe it's due to this operator of the center bias. It kind of floods the image. Here it doesn't really show it so well, but in the results on the web page, their saliency maps are kind of a little saturated. Backwards, you can see these attention maps. For each of these attention maps, for each blob, for each object, connected object, I was going to find the center of that object, find the centroid of that mass. At that point, apply two-dimensional Gaussian kernel that had a standard deviation related to the mass of that blob, and then do a linear combination between the attention map and the new map that I have. And so you can see here that AM is the attention map, and then beta is a parameter, a constant parameter that we could use to vary from 0 to 1. 0 would take the whole entire the prior attention map S, and then 1 would take the entire object-based center bias map O instead of S. And so that performed pretty well. And we'll go into the performance a little bit later. But so BMS was implemented in C++, and it uses the OpenCV computer vision library. This is very easy to use once you get acquainted with OpenCV, and I just provided the BMS code in line. I put comments in the code to mark where I modified it, and so to be able to detect those objects, and get figure out where the objects are and find the centroid of each of the objects in the attention map, I had to download CV Blob. It's a third-party library that works with OpenCV, and given a binary image, it will find the blobs, find the centroids and the masses, and I could use that for centering the Gaussian kernels about those objects. And then OpenCV was very easy to apply the Gaussian kernels and do that linear operator about those. So you just kind of go into the evaluation. The MIT Saliency benchmark uses a handful of metrics. They use area under the curve. They have a couple different implementations. They have the Judd, that's one of the researchers, have his implementation, Borges' implementation, and then I like to call that sauce, but it's the shuffled area under the curve. And so each of those are trying to measure the area under the ROC curve, or the receive on the receiver operating characteristic curve. And so the true positive and the false positive are a little bit different for each of them. The true positive is given some threshold at fixation locations. What is the rate of the saliency map that is above that threshold at those locations? That's your true positive rate. And then your false positive rate is varies from each of the different algorithms, and I go into further detail in my paper about those. And sim is the similarity between the two distributions, or this is also known as the histogram intersection. So they just take the histogram and find the common the similarity in each of the bins, and they sum that out to get the similarity metric. And then EMD is the Earth mover's distance, and I'm not sure how much audio you got. So I'm going to start over on the slide. I apologize. I think I went off the screen and it stopped recording. So MIT Saliency Benchmark uses a couple different metrics. I think, like I said, they use the area under the rock curve, the receiver operating characteristic, and they have 3 different algorithms for that. They have Judd, Borgi, those are 2 different researchers, and then they have the shuffled area under the curve, or SOS. And their true positive rate uses the true positive rate is using at each of the fixation locations of the truth data, given some threshold or varying thresholds, does the what is the ratio of the saliency map that meets a certain threshold at each of those locations, and that's the true positive rate. The false positive rate is slightly different for each of those algorithms. I go more into detail in my paper about that. SIM is the similarity or the histogram intersection. EMD is the Earth mover's distance. That is calculating basically the cost and how much work it takes for you to transform the saliency map into the fixation map. And so higher score similarity is good. A score of 1 is perfect. 0 is no similarity at all. EMD of 0 means it's a perfect match. There's no transformation necessary to go from the saliency map to the fixation map. Also, for the area under the rock curve, a 1 is basically all the true positives with no false positives, so that would be a perfect score, with 0 being the minimum, where you're having all false positives and no true positives. And then CC stands for the correlation coefficient, so that's similar just to the Pearson's linear coefficient. So a score of 1, here we're taking the absolute value of the correlation coefficient, so 0 is no correlation whatsoever, 1 is highly linear correlated, and -1 is inversely proportionate linear correlated, but we take the absolute value, and so 0 to 1 is the scale here. And then 1 second. And so the NSS is the normalized scan path saliency, and that is looking at each of the fixation locations. What is the mean value in the normalized saliency map at those locations? So a higher value of NSS is better. It's kind of like a raw score. There is no maximum to that. So those are the metrics that they use, and I provided some of the results of the different algorithms presented before. Unfortunately, deep gaze and deep fix are neural networks, and the source code is not open source, so I could not actively test them and evaluate them in my MATLAB environment. To go further into the evaluation,
here I provide the metrics.
I use some MATLAB scripts that MIT
you can
provided.
see that
the scripts were a little
deep gaze has a
lot
larger
on those. I
Earth
changed
mover's
things
distance
from doubles
than
to
the other
floats,
2
algorithms for the MIT 300 benchmark, and that's
and a couple
due
other
to the
things.
saliency maps kind of have that flooded view, and
I
there's
then
a
created some
large, you have
MATLAB
to do a
scripts
large
to be able
transformation to remove
assess
a lot
a
of that
whole
extra
entire
noise
data
to
set
get
of
the fixation map.
similarity
But it does
maps.
have a really high score
And
area
so
under the curve. The scripts
Judd,
that MIT
and
provided,
Borgi.
they were only evaluating a
And,
single map and a single
That's just due
fixation
to
map. So my scripts say, give
it's
me a
good neural
directory
network,
with all
and also
of
it's
the
been known that even
saliency
if
maps
you
and a
do
directory with all the fixation maps, and then it
have
performs that analysis for you,
just
opens the
a
images,
Gaussian blob at the center
etc.,
of the
and then
image
gives you all the
with
scores
no other
out
features, it does score
for each
very
of the images.
well on
the
area under the curve.
So some lessons learned is that the metrics are computationally complex. It for my simple my down I even down sampled the saliency maps. I brought the resolution from like 1080 by 1920 down to like 600 to 800, and even then it took an hour to go through 2,000 images. Whereas it only took 12 minutes to generate the saliency maps, evaluating the metrics took a lot longer. Specifically, the area under the curve for the Judd and the Earth movers distance, those take a long time. So I did some improvements to try to bring it down to an hour. Otherwise, it'd be several hours. And so downsampling helps with saliency maps to help with computation time, but it does lose accuracy. You should not use this for an absolute performance against different models. You should only use it as a relative performance. So if you have to evaluate everyone given these downsampled saliency maps, and then you can use that as a relative performance to see if you've improved. And now you can start prototyping your algorithm before submitting it to the database, to the MIT benchmark for real numbers. So some preliminary results. The center bias. This is results of my BMSS algorithm. The center bias really did help out a lot. You can see on the left column here we have human eye fixations. The middle is BMS and the right is BMSS. You can see that human eye fixations definitely was necessary to help focus the saliency map. You can see that BMS for like the second row, it's just all over the place. And so your EMD, Earth Mover's distance, is going to be very large to transform that saliency map into the human eye fixation, which has a hotspot near the center. And so you can see I kind of have a Gaussian blob near the center of the BMSS algorithm. It's simple, but it works and does the job. And then I even that combinator, the linear combination, took less of the BMS algorithm, less of the BMS saliency map, and more of the Gaussian blob. And so that filtered the rest of it, and that actually brought down our Earth mover's distance quite substantially. We see like a 38% performance increase in Earth mover's distance, and the similarity even went up quite a bit. So these are using my experimental CAT 2000 metrics. So again, probably not good to use these numbers for like an absolute performance. We would probably need to submit the data back to MIT for processing. Now, these are using the training sets, and that was necessary so that we could actually evaluate against truth. It would be interesting to see it with the actual test images and see how it performs. So there was definitely an improvement here. I mean, correlation coefficient went up 75%. The area under the curve and the normalized scan path saliency, they did get decreased, but I feel that with some improvements, I'll go over in the limitations, we could probably see a little bit better than that. So the implementation center bias are a little immature. The Gaussian kernels are just they're combined linearly, and that's kind of giving just a Gaussian blob. There should be something more of a gain operator where it takes into account of both of them and does more of a multiplication or convolution than it does just an addition and normalization. That'll probably help with the other features, and it will also help with the other scores as well further for better performance. And then I kind of noticed this in the BMS algorithm, but there's excess features that are detected. And looking at the object-centered bias, object-based center bias paper that I was talking about earlier, given the way that they were evaluating their algorithms, they didn't pick up every single anomaly in the image. They only picked up just the raw big images in the player into the image. So if we had better ways to detect objects and get rid of all these excess features that are being picked up using this Boolean map thresholding that BMS is using, I believe we would start seeing a little bit better in performance. So that's something that was inherited in BMS, and I was not planning to tackle with BMSS, but that would definitely improve performance. So some conclusions. I was able to go through visual saliency and understand what it is, kind of see what were the top performing models, what breakthrough research is. Like I took this center bias research and applied it to BMS to get BMSS. We saw a substantial performance improvement. That's fairly new research that's going to be presented, I think, this month in December, and I was able to use and create some C++ and MATLAB code to be able to change the algorithm, test it, change it, test it, etc., repeat until I got a performance that looked good. And I would like to do further research on how to apply uh, these algorithms towards robotics and machine learning. I feel that we're still only looking at raw images. We're not even looking at video sequences yet. But if we started looking at those, I think we're going to start seeing some really interesting results, and that would kind of expand the area of visual saliency. I didn't really do a lot of research, didn't have time to see if anyone's doing that, but I would like to research further on how to do that. And then I would also like to fine tune BMSS a little bit more, fix the Gaussian kernel limitation I spoke about, and then submit the saliency maps to the MIT saliency benchmark to see how I perform against the other models out there.